My name is Josh Johnston. I feel like I should be like tending bar on a beach somewhere or doing tech support out in the lobby. This is kind of an interesting kiosk setup here. So I'm going to be talking today about moving a platform that we have moved at Kount from our original implementation, which was in scikit-learn, over to Spark, using some of the tools that actually we had a couple of people down here at this conference last year that they learned about these tools, and we picked them up, started using them. So I am the director of AI science at Kount. We have a cross-functional team with about a dozen members on it for specifically focused on machine learning and artificial intelligence. It's part of our larger IT organization. Today I'm going to talk about model lifecycle and a little bit about our specific model. That's not the intent of the talk. I just want to give you a little context about what we're trying to do with our model. But mostly I'm going to be talking about the process, how we train it, and how we have the tools around it that we need to have good model governance. So we started relying heavily on an analytics database and scikit-learn. That method worked. We made it a lot better as we moved to using Apache Spark and HDFS. And the recurring theme here is going to be talking about model governance. And I'll talk about what I mean for model governance. This is a slide. This is a slide out of Microsoft that I think is a really good representation. It's unfortunately a lot to put on this slide set in this big of a room. But you see we have a data science lifecycle that begins up at the top with a business understanding. And the purple stuff on the left side, this is modeling. The stuff on the right side is data, where we get the data, how we interpret it, how we clean it up. You can see there's a lot of lines that go back and forth between these because there's a lot of different cycles, right? What data do we need? Well, give me some data, I'll figure out what I can model, then I'll figure out what other data it turns out that I need as we loop back around. And then whatever we come up with as a result of these pipelines, the data we have, the modeling that we're doing, it has to get to deployment, has to get to some place out there. And for Kount, that specifically means deployed in a real-time environment with streaming data. So I'm going to focus mostly on modeling and our pipelines for building models. We have another talk. Noah Pritikin, who's one of my colleagues, is here. He's talking this afternoon. And he's going to be talking about the production side, how we move our model into production using MLlib and some of the other processes that we've built around that. So if you think about this, this is kind of the first half of where our model comes from and the traceability to know where we generated a model. And he'll be talking about how we get that model into production and know what it is that we have running in production. So when we're doing modeling and thinking about life cycle, there's a few things that are really important to me. Configuration management, again, speed, right, how fast this thing runs. The accuracy, whether we're getting the right answers or not. We can get really fast answers sometimes, and they're just not right at all. And then validation. The distinction here about accuracy and validation is that with validation, we're really talking about making sure that whatever we thought this model was going to do in the real world, where the rubber meets the road, we're still getting the performance that we expected. And we think about this in terms of model governance. Model governance is a new concept, a pretty new concept. Data governance is I think, a more robust concept that's been around for many years. More and more of us are caring about model governance. It is amazing to me as I go and talk to people where I say, you know, I used to have this process to figure out what model I had running in production. I would go ask our operations guy, what's the file name on the model in production? And he would go look and tell me. And now I would know maybe what model is running in production, and I could go back and tie this into my logs. And like, that's a terrible story. And it's always funny to me when I tell that story, how many people I see nodding and being like, yeah, I've been there, or worse, I am there. You know, we all start somewhere. At Kount, we work with a lot of banks, and our bank partners care a lot about model governance. So I have to fill out questionnaires where they ask me a lot of the questions that I have here that we need to be able to answer. Simplest is, what model are we using? And it's a little more than just knowing the file name. Do we understand what the assumptions that were made, what data we generated that from? If we did sampling, how did we get to the subsample data that we used to train this? If we did class balancing, how we selected for that? What metrics we used to decide that this model was going to be working well? What parameters did we use? What version of the code did we run? There's a lot of those kinds of questions, and it's easy to get focused on that, to get focused on the model that's in production. But if we think a little bit more broadly about how we trained it, we also need to answer the question of, we didn't just train one model, right? We trained a whole lot of models. So why did we pick this model instead of all of the other models? It's not enough to just have traceability on the model that survived to production. We also need to understand the decisions that we've made to reject other models. And again, this can become very important for a lot of different reasons. Just for our own benefit, for accuracy, make sure we're doing the things that we think we're doing. It's going to become important when you're talking about legal issues and exposure to liability, not just for ourselves, but for people who use our product. Another question we need to be able to answer is, how well does it work? And that's both our expectation as well as reality in production. And all of these are hard enough questions, I think, to answer sometimes the first time. But we really need to be able to dig into the meat of the why, the context, how we got there. And all of this, I don't want to act like the whole point here is to survive a model governance review and be able to satisfy some bureaucrats or some management. Fundamentally, what we're doing with our AI science group at Kount is science. And science is repeatable. If we're just building things and putting them in production and we don't really understand what's going on, we don't have that repeatability, and we have a limit to how much better we can get. So if you want to have repeatable science that's at the quality that you could go out and publish this and have it survive peer review, which I think is what our expectations most of us as data scientists have on ourselves, then we do need to be able to answer all of these questions that are there just to be able to satisfy ourselves that we really are making the progress that we're trying to make. So where we come from at Kount, I'm going to be talking about a fraud detecting model today. And in particular, Kount, we work across a variety of protections from digital fraud. So we protect from fraudulent account creation, account takeover fraud, transaction payment fraud, authentication friction. The model I'm talking about today is in the transaction and payment fraud space. So our customers are online merchants. We do card not present transactions, which incidentally means that the card is not present at the transaction, but card not present is like a term of art. It sounds like something you just made up, but it's a real term out there. And most people don't realize, but the liability for card not present transactions actually sits with the merchant. So if somebody goes and buys a television at an electronics store, and it turns out that they use a stolen credit card, the bank generally eats that cost. If they go and buy from that electronics store's online website, that electronics store eats the cost of that television. So our merchants pay us to help them understand whether they should approve, decline, or hold for review transactions. What this means in production is I have substantial throughput here. My background is in robotics and unmanned systems, where you might be streaming 1 million data points a second, and that's not really that big a deal. We process 30 to 100 transactions per second. The important thing here, I think, is tying this with our low latency requirements. We operate in the loop of the purchase. And a lot of our customers' products, they're delivering digital goods, so the delivery is instantaneous. And that means that we have to maintain a 250 millisecond end-to-end latency from when the query comes to us to when the result goes back. When you're buying something and you see the thing thinking and you can't tell whether it took your credit card information, we're going to blame most of that on the bank, but a quarter of a second in there is maybe our fault. So this has to go very, very quickly. And when you add up all of the other things that need to happen as part of this pipeline, my team in machine learning, we have maybe 15 milliseconds to run end-to-end, run our models, and come up with an answer. This is where our AI and machine learning fits into the broader picture of this payment transaction fraud protection pipeline. So a merchant lives over here on the left side. You go and buy something for that merchant. Transaction details that you put in on the checkout page, as well as some information that we can collect passively about the device, is pulled into our system. We execute our AI and machine learning. We put this transaction into the context of a lot of other transactions, a lot of other things that are going on. That's the global transaction data. It's really important that there's very rarely enough red flags that you can decline a transaction just looking at a single transaction. Like, do I know if this is fraud or not? It's hard to tell. We have to look at patterns. We have to see what's been going on both with that merchant as well as other merchants across our platform to be able to find fraud. It's inherently organized crime, and there's a lot of network effect that needs to be collected. So that's where our model lives that I'm going to be talking about. In particular, I'm talking about the model that's behind our Boost technology, which is a supervised machine learning algorithm. We take the results of this, as well as hundreds of other data points that we generate out of these machine learning algorithms, and execute a merchant policy layer. So merchants can decide both how much risk tolerance that they have, as well as specific policy rules around things like gift cards or promotions, or whether they're willing to ship internationally. And we come up with the decision, approve, decline, or review, send that information back, as well as hold a bunch of it for business analytics to come back and look at later. And again, this whole pipeline occurs in under 250 milliseconds. So this is the data that I have access to. I have a lot of data, which is just fantastic as a data scientist. This is about 3 months of transactions. This is everywhere in the world that the device was that Kount saw a transaction from. So there's a few 100 million transactions represented here. You can see we have extremely good coverage around the world. This is roughly the data that we use to train our supervised machine learning model, about 3 months of history context. And we released this model, Boost technology. We released it about 1.5 years ago. This is just some of the feedback that we received, all stuff that makes me feel really good. I can go take to my management and show very clear improvement. You know, we have people saying things like reducing manual reviews by 20%, 200 hours a month, approving an extra 3,000 transactions and $1.2 million per month. But the ones at the bottom, actually, these kind of qualitative ones, are the ones that surprise me. How often when I'm talking to our customers and they say, this makes me sleep better at night. I used to worry, because fraud is a 24/7 thing. That's what e-commerce is, it's 24/7. And so when a fraud manager is going to sleep at night and they're thinking, I got to get up and I got to go clear through my review queue because I'm going to have a whole bunch of good orders sitting in the review queue I have to clear. They don't like that. This tool has helped them be able to feel like the automated decisions that are being made are satisfactory so that they can sleep at night. So that's all kind of the business side. Again, if you think back to that Microsoft diagram that I started with, there's this business need that everything in data science begins with and works in service of. This is more of the technical view. So we have a feature engineering step as part of Boost. We pre-process a lot of data. That's really where our secret sauce in this algorithm is. That's where we take that 3 months of data and we do some things with it that make it take up about 200 gigabytes. That all has to be held in memory to be accessed very quickly at the time of our transaction. But the model itself is pretty vanilla. It's a random forest. We have about 250 trees, 100,000 nodes per tree. So it's a very complex model. And we didn't just do that for fun. We actually found that as we continued to increase the complexity of this model, we continued to capture real value, not just overtraining. So serializing this model itself is about 1 gigabyte. And that's some of the challenges that we have is even just kind of moving this model around. It's not the kind of thing you'd want to check into Git or something like that. And then, again, we have about 150 features after the feature reduction step. The cardinality of raw data, most of it's tokenized. It's things like email addresses and names. So the cardinality is billions of unique values, depending on how you want to think about those tokenized features. If you were to one-hot encode them, it would be billions of features. After our feature engineering step, we have about 150 features. We run 60 million observations through the model, through the random forest itself to train it. And here's how we started that. We started using scikit-learn, and our process looked something like this. I use process loosely because it was ad hoc, and a lot of these steps were just done manually when needed. So we had an analytics database that had this data sitting there available. We would go in there and running on a box. So this box that says model training service, that's running on a single computer because we're running scikit-learn. It's all living in one place. And we started jamming a lot of resources into this box. So I kept saying, I need more RAM, I need more RAM. We got 400 gigabytes in there, and still, to process this data, we're running like a terabyte deep into swap, which is just really super for performance. Getting things in and out of this database. We're talking about hundreds of gigabytes of data. So pulling this out is just a process that takes hours, doing this in a single threaded way. Computing those lookups that I talked about in that feature engineering step, we did that in the database. Then we had to get this information back out. This analytics database supports other production uses at Kount. So it supports both tools that we use internally, but also it supports customer tools. So our customers can run queries about their data in this analytics database. So all of this time that we're just pounding this database was not making us friends with the data analytics team. The other challenge we had here is that this is all sitting in memory. So if there's anything bad happens during this process, you're back to square one. You know, we have to go back and start at the beginning and start pulling all of this data back out of our analytics database again. And then we finally get around to training our model, which especially having to swap things in and out of disk would take 24 hours. So there's a limit to how many different conditions we could test or what kind of a parameter grid we could search. At the end of that, we've logged some data about where this thing came from. A lot of data we felt like at the time so that we understand what the parameters were that were used, how we built this model. It turns out it was never all the stuff that we really should have been logging. And we stored that out as a pickled object. So we serialized it out of Python and stored it away. So this process, like I said, I put 2.5 days on here, but really it depends on how many times something interrupted this in the meantime as to how long it would actually take to run. So what worked with this process? Well, we trained a high-value model. All of those comments that I had up on that slide about the impact we had to the business, that was all made with this approach, with this technical approach. So it worked. We got serious business value, impacted the bottom line of the business. I tried to come up with some other things, and this was all I had for this slide. So what doesn't work? This one was a little easier. It's time intensive. As I said, any error in this process, we have to restart the whole thing. We're burdening this production analytics database that has other things it's supposed to be supporting. The pickled model, and Noah's going to talk more about this in the afternoon, but this pickled model really tied us between our training environment and our execution environment, because we serialize the thing from the training environment. Later, we unpickle it in the production environment. We have to have like the exact same version of all of the libraries that touches. And if we want to update that, we have to first update it in our training environment, and then we have to now do what should be a pretty straightforward model push to production is now like a full maintenance deploy. And one of the things about the way we do deploys at Kount is that we have 0 planned downtime. And we have 4 nines of uptime, 99.99% of uptime. So we have something like 30 minutes of downtime a year, and it's all unplanned. So these deploys have to happen. It's like, I don't know, it's like freaking magic to me. But when you start creating these dependencies where pushing a model involves also having to go and update libraries, it probably won't surprise you to know that in all the time we had scikit-learn models in production, we never updated the libraries in that environment. And also our traceability was provided by logs. So again, I could ask, what model do we have in production? Make sure I know which one we have in production. I can go back to the logs and I can find the information about how we built it. I've got no context. I don't know what we were doing. We document whatever we can. We write narratives using Confluence where we write stories about what experiments we're running and why and what we're investigating and why we're making the decisions. But tying this back to the actual log files that we have is limiting. And as I'm saying, these are ad hoc experiments, and we don't have good configuration control on it. So yeah, all of our code is checked into Git. But what does that mean? Right? What data are we using? What things have we changed? There's a lot of stuff that goes on besides just knowing that your code is some version of the code. So if we think back to these governance questions that I brought up and said, this is, to me, every questionnaire I've ever seen about model governance, I distill it down to having good answers about these questions. And I've got poor answers for most of these questions at this point. At the time, it felt like we were doing a pretty good job because, again, I had answers. I can go back and look at these log files. I have a lot of stuff. But it's nothing like where we ended up. Or I should say where we ended up so far, because this is, of course, always an evolving thing. So we decided we were maxing out what we could do with one computer. So we decided to switch to a cluster. We run Spark and HDFS on. More resources available to begin with. Also having this attached HDFS service gives us some advantages as we get to our new process. So we still begin with this analytics database. This is really our database of record for all of our batch processing. But now we're pulling that data straight over to HDFS using sqoop. We can support multiple connections, and we can run this much faster. We hit the database a little harder, but for less time. We could also tune this to trickle the data out more slowly if we chose to. We found that our business impact on our other operations, it was better for us to hit it a little harder for less time. So we get everything over to HDFS, and that's it. We're done dealing with pulling new data out of this analytics database until we decide to go back to the beginning of this process. And now we're building all of those lookups, the feature engineering steps that we were doing. That all happens now on our Spark cluster between Spark and HDFS. We get the lookups that we need to have for that, and then we train the model. We're doing that with Spark ML. And we're using MLlib for our production environment. So now we're zipping up this model into an MLlib pipeline. I'm probably messing up the terminology there. Again, if this is the part that you're interested in, you can just walk out now and come back for Noah's talk this afternoon. We get that out there. And then also, we save that into HDFS. And then we're using MLflow primarily for, I'd say, logging, but providing this context and configuration management. We're using Luigi for a data pipeline to manage pulling this data and getting this pipeline automated from beginning to end, because there's multiple steps here that all need error checking around them. And I'm going to talk here about, well, how do we go and execute things on this cluster? We do this from a data science perspective, primarily with Jupyter Notebooks. And Jupyter Notebooks are really interesting to me because there's everybody either loves them or hates them. I guess I kind of fit a little bit in the middle. I have a love-hate relationship. Most of the criticism that I see of Jupyter Notebooks are things that you could do with them, not things that you have to do. So we recognize that Jupyter Notebooks allow you to do all sorts of really dumb stuff. And we put good practices and process around that. My feeling is that if you are relying on your tools to enforce good development practices, you probably don't have very good development practices. So that being said, though, we're always very careful about this, but keeping these practices independent of our tools. And we use a process as we get to maturity that, and this is a vague process. You'll notice I didn't label the axis here of time. But when we begin, we don't really know what we're doing, right? We've got a vague idea of a business application we're trying to make some impact on. We go and start exploring the data. And our data scientists are definitely doing that in Jupyter Notebooks. And we're moving very quickly. However, we're already using Git for configuration management for everything. Even if this is your own personal code and it's ugly and nobody ever is going to understand it, all of that still gets checked in. We're very, very rigorous about that. As time goes on, a lot of these projects just die, right? A lot of these ideas are just, I'm going to build a notebook to look into something, and then it turns out it was a bad idea. I'm done. But if it's going somewhere, as this process gets more robust, we start to pull functions out, and we start to objectize code, and we build Python packages. Now we're calling into these packages from our Jupyter Notebooks. And eventually we get to the point where we have enough stability in whatever it is that we're doing that we can actually convert to using a PySpark application. And now we're just running that instead of running the Jupyter Notebook. And then finally, we can now refactor and harden this code and add in automation. And that's our last step, so that now it's not even data scientists or machine learning engineers that are running this. We've fully operationalized this code. So with this approach, using Spark, it's faster, quite a bit faster. Failures restart in the middle, which makes it even faster. So if we have some kind of an issue, we don't have to go all the way back to the beginning and pull everything in memory again. We're just going back to whatever the last step that's successfully executed and saved into HDFS. This is also reducing our burden on our production analytics database. We can redesign our experiments without penalty. So it used to be I had a 20-hour process before I start running my experiment. So I have to plan out exactly what parameter values I want to search before I go and start training models with these different parameter settings. And if I guessed wrong and I have to stop, I got to change it and go all the way back to the beginning of this process. Now if we see that an experiment is running and it's not giving us the value that we expected, we're changing a knob and nothing's happening, then we can just kill it and restart and not experience so much of a penalty because, again, we're only going back to where we had things partway through this pipeline. Really important for operationalizing these models, we're using MLlib to decouple that training environment from the production environment. So when our model is running in production, it's running in this MLlib wrapper with an endpoint. So it can be doing whatever it's doing. It doesn't impact any of our other code that's running on the production side. What still doesn't work? We still have a lot of Spark tuning issues. There's non-deterministic behavior. We have errors that kill things. This costs us a lot of time. It's an area we're actively working on. And also, and I think this is actually really interesting, the stuff that we've heard today about things like Delta, is we still don't have good configuration control on our data. So we have a pipeline that we run to go fetch this data, and we can go run it, and we know it doesn't change until we go run that pipeline again. But there's changes that are happening in our data analytics database, our analytics database. Those changes are happening all the time. So I cannot go back and recreate a historical model with the exact conditions that I had at that historical time because I don't have a data representation. So this is something that we've been thinking actively about. There's multiple tools out there, and I'm excited to see what, how Delta may fit into that. But this ability to get that management back onto our data, that's a piece that we still have missing. So I'm going to talk a little bit about those specific tools, Luigi and MLflow, and how we're using them to answer these model governance questions. Like these are the things that keep popping back up for me because this is really the motivation when I'm looking at this process, to get things repeatable so that we're doing real science and not just being craftsmen or artisans that are producing a model that nobody understands. I'm going to break this into kind of two pieces. One of them is traceability, and one of them is traceability for the data. And one of them is traceability for the experiment, the configuration, and our expected accuracy out of this model. And we're using Luigi and MLflow for these two components. Luigi, we can set up all of the discrete actions that we do to build our data. Again, we have a relatively complex feature engineering process where we have a lot of processing that we have to do, and then we have to take a bunch of our transactions and go look up into those pre-computed values. So there's multiple steps that we have here. We can define all of these with both the code that's supposed to run, as well as validation, what kind of an end state we can get to, whatever testing that we're going to execute to make sure that that completed properly. And then Luigi allows us to tie this together with a dependency graph. So we can say, here's all the pieces we have, and here's the order that these have to execute in to give us the final result that we have. This is an example of something that's running, and you may not be able to see it all, but the ones that are yellow here are pending, a couple of them are done, and there's one that's actively running. So each one of these boxes is, again, some discrete data transformation that has to happen. And if it fails, doesn't pass our checks, or it errors out in some way, then it will go and it will automatically rerun so that we'll get the right data across. And this was a huge thing for us. It used to be, I have to kick something off because I want to train a model tomorrow. I'm going to go grab some new data. So I go kick some code off. I check it. I mean, I'm sure like a lot of people in here do this, right? Then you go home, and you check it as soon as you get home. And you're like, OK, it's still running. And then like you eat dinner, and then you check it again after dinner. And then you're about to go to bed, and you check it again when you go to bed. And you wake up first thing in the morning, and it died while you were asleep. That's always the way it works, right? So with this process, we have a much higher likelihood that when you come in the morning, that data pipeline that does still take hours to execute has executed successfully. And we also feel good that it did execute correctly. And again, we have like a nice traceability to that it's not just like, I forgot what I kicked off last night, but it sort of looks like the data's there, so I'm going to go train a model with it. MLflow. So MLflow, if you haven't dug into it, is a great tool, I think, for managing experiments. This is a set of experiments. I guess you could think of this as one experiment. These are different configurations of the same model that we're training on the same data. So here we're doing a parameter grid search. The columns, this is a random forest model, so the columns are things like the maximum depth and the impurity measurements that's being used. So we can tweak each of these knobs, do a parameter grid search, and we get to see all of those settings for this whole experiment, as well as the end result for each of these models, because each one of these lines is training a different model. And we can reserve our training data, reserve our testing data, train the model, test against our testing data, and we can save that information off. Not only does this provide great context for the experimenter, because these experiments can still take days to run. And when you come back and you're like, what was I even running? Well, you can just see this and you can know. As a manager, this is like fantastic. I'll be sitting here Sunday night, I'll be like, I wonder what the runs over the weekend have done. And I can go look at them, get the context, understand what I think I'm seeing. And then when I go in and I'm talking to folks on Monday morning, I have that context. They don't have to go and write me up a report that says, like, here's the things that we looked at, and here's all the outcomes, and this is the path forward that we think we're going to take. We just sit around and we look at this data. And this is preserved for us, forever. So later, when I take one of these models and I put it into production, and somebody comes back and says, what model are you running, and how did you come up with it? I don't just know this is the model that I was running. I actually know the entire larger experiment that it was part of. So I know what I was doing and how it compared to the other ones. Lets me test any assumptions that once I get in production, some of the assumptions I made I may no longer believe. We can wrap up a bunch of artifacts with these experiments. So we put things in here like ROC and precision recall curves so that we can look, not just wrap it up into one number, looking at an area under the curve, but we can actually go and check these curves themselves. We put the model itself as an artifact. I mean, sure, it's like a gigabyte, but whatever, just jam it in there. So I can go back, and if I ever have, again, a question about exactly what I'm running in production, I can even go do a checksum test against exactly this same model from these experiments. We put in the MLlib container, we also put in a test frame. And this is something we started doing that I think is a fantastic idea that I would strongly suggest. So we put some data with an expected result in the MLlib model itself, and that's an artifact here. So when that model gets loaded into production and unpacked, the first thing that we can do is run that test transaction and see that we got the same answer. And that's another check that we can have on our production software to make sure that all the data fields are all lining up the way that we expect them to. With MLflow, we can also take all of those experiments that I was showing, and we can easily make plots. These were things we used to do by hand. So in this case, we're doing a feature reduction experiment. So the x-axis here is the features, and the vertical is some measure of quality. Looks like the area under the precision recall curve. So you can see that when we're using our full set of features, about 180 features, I think, on this one, as we cut back the number of features, we see what we might expect. We see not a lot of change, and then at some point we start eating into the quality of our model because we're reducing features that are still adding significant value. There's a couple dozen experiments here. And this would be the kind of thing that I used to have to go and write like a sed script or something to go pull out of log files, to go pull the accuracy out of each one of these log files, and then go manually build this plot. And this is stuff that now I can just see on a Sunday night when I'm looking at this. So a lot of value that I think we get out of this. And it just makes you feel a lot better when you do have to show your traceability, that you're not just running an ad hoc shop where the data scientist can figure it out, but he doesn't have the answers at his fingertips. I've always felt like when you're answering governance type questions, especially if you get audited, you don't want to have to answer anything. Like, you don't have to explain anything. You want to just be able to say, you know, what model am I running? Point, right? Everything should be able to be answered with a point. I'm running that model. You know, how did I train it? It's right there in MLflow. So again, as kind of wrap this up, we use Luigi building these data pipelines with error handling. It's repeatable. It's self-documenting. All of our data transformations, we can understand where that data is coming from. MLflow documents the parameters in our model. The trace of the code and data use. I guess I forgot to mention one of the other things we do. We take the git hash, you know, the revision hash, and we put that in as an artifact, so we know what code we ran. And I know you're all thinking right now, but how do you know the data scientist didn't change the code after he checked it in, right? Yeah, we thought about that. So we take the whole code, and we make that an artifact. So we just save the code in with the model. So if you have any question about exactly what was run to build that model, that's all forever linked to that model. We store the model and these configurations as an artifact. So now if you go back to these questions, again, I can answer each one of these by pointing at one of the pages that I just showed you. I don't have to think about it. I don't have to write an explanation. It doesn't come out of my mind. It's all there, which really helps us with our governance process. So the benefits that we have, this runs faster. Our failures restart in the middle. We're reducing the burden on this data analytics database. We can redesign our experiments in the middle without taking any penalties because we can restart easily. And MLlib is decoupling our execution from our training. And I would strongly encourage you to hear Noah's talk this afternoon on how we use MLlib. And there is this much process or more around how we manage what is actually running in production. At this point is kind of where I hand over this model to Noah and I say, here is the best model. Now, you know, go off and do all your DevOps production magic. So I think I left like 2 minutes, if anybody's got any questions. Question? How do we integrate Luigi and MLflow? Yeah, so I got to be honest, I didn't have to do that work. I had people do that. They're both pretty straightforward, though, to my understanding. So Luigi ends up basically wrapping up whatever we wanted to write. So the things that we were running ad hoc, if going back to this slide about our development process, that was harder to get to than I thought it was going to be. When we start, you know, we're moving data around and we're doing this very manually out of notebooks. At some point, we build these into applications, and we get to the point where we're running the same code to move data around. Then we can wrap that chunk with Luigi, put whatever error checks we want to have around it. So that's where it goes in our process. It's this automation line at the bottom here. We take the existing code. It's not like we have to go rewrite it and do it a different way. We take the existing code and we write this wrapper around it to interface with Luigi. And MLflow works in a similar way. We have to add, where we might have had a parameter grid search, we have to add what parameters we care about, and we push those to MLflow, which is running as a service on our Spark cluster. So it doesn't matter where on our cluster we are, we can talk to that service because it's a web service. And we push those parameters. When the model gets done, we push the model and whatever else we want to collect into an artifacts directory, and it gets sucked up by that web interface. So integrating these was very straightforward.
All right. We don't have time for any more questions, but Josh will be hanging out. I'm sure he'll be happy to take more questions offline. Please do not forget to rate and review these sessions in your Apache Spark Summit app. With that, give a round of applause to Josh.
Thank you.